Welcome back, trigonometric friends. Today we're going to talk a little bit about the half angle formulas. If you turn to, if I ask you to turn to page 407 in your workbook, first of all, you might say no, but if I ask you again, like really nicely, maybe you would, and you'd find some notes that outline some of the discussion points we're going to have. Here are the half angle formulas. Basically, there's one for each sine, cosine, and tangent. The sine half angle formula is plus or minus the square root of 1 subtract cosine theta over 2. You'll see that the cosine half angle formula is very similar, the only difference being that instead of a subtraction, we have an addition. And then because the tangent ratio is sine over cosine, right? We remember that. The tangent of pi over 2 could be rewritten as the sine of, not pi, but theta over 2 divided by the cosine of theta over 2. We could just put these two formulas over each other. And what would happen if we did that? Well, you are allowed to divide a root by a root. We're going to use that algebra property a lot. But pretty much these 2's would cancel, and you would just get the 1 minus cosine over the 1 plus cosine, which is exactly what we see in that tangent formula. I'm going to actually talk briefly about where these formulas come from. The derivations actually come from the last formulas we discussed, which are the double angle formulas. There were 3 different variations of the double angle formula for cosine that we found. These were them. And the ones that we're actually going to use are not the original one. This guy, the cosine squared subtract sine squared that I'm erasing right now, that was the first one we found. The reason that we like the other ones is because we only have a sine squared in one of them and we only have a cosine squared in the other. And that's going to allow us to do a little bit of algebra. And in fact, the algebra is right in front of you. You can see exactly what's going down here. I'm going to do a little simple mathematics with the first one. I'm going to take this negative 2 sine squared theta and add it to the other side. I'm going to take this cosine 2 theta right here, and I'm going to subtract it to the other side. Then let's get rid of this 2 by dividing everything by 2. That's what we did right there, right? Of course, we still have sine squared, so how should we get rid of that? Oh, I know. Let's take the square root of both sides. Now, one thing to keep in mind is that when we take the square root of both sides, we do need to do a positive or negative root. When you take the square root when you're solving an equation, you never know which root, maybe both, are going to be needed. And so you do need to include both of those roots. That's why those plus or minuses are part of the formulas that we end up using. The algebra on the other formula, very, very similar. We start with simple adding 1 to both sides to get rid of the negative 1, and then from there we divide by that 2 to get rid of that, and then of course take the square root again. And these are basically your half angle formulas for the most part. They're not written in half angle formula format yet, but that's a simple trick that we need to do to take care of that, which is in substitute pi over 2 for theta. Okay, so if we did that in slightly larger print, let me show you what these would look like. Here's the half angle formula for sine. Here's the substitution of pi or theta over 2 in for theta, which means I have to plug theta over 2 into the equation for theta, right? We've got substitution for theta over 2 here and here. But what happens in here is the 2's cancel. Fantastic. And that leaves me with just cosine theta. So what this formula really allows me to do is it allows me to find ratios based on an angle theta that I would actually be finding for theta over 2. Very similar work on the cosine formula. We substitute in right here our theta over 2. When I put that theta over 2 into the formula, the 2's cancel, leaving me with just, once again, cosine theta. And that's something you should notice about all of these formulas. The only ratio you need in a half angle is the cosine ratio, which is kind of nice. Kind of nice not to need a number of different ratios. For us right now, there's a limit to how much these formulas can really help us. They can help us. I mean, there's no way that you can look at the unit circle or your table of values and say, oh, I want to find the sine, cosine, or tangent of 22.5 degrees. That is not an angle that you could find on there. But if I doubled 22.5 and rewrote it as 45 degrees divided by 2, now it's written as a half angle, and I could, right, that's our half angle, I could base my ratio on 45 degrees as the theta value, and I know what cosine of 45 degrees is. And so that's kind of how we use them. There's much more powerful uses of these in higher levels of math, like calculus and beyond, where you're using these formulas to help you derive or solve problems in which substitutions are necessary. It's hard to get into that right now, but why don't we go ahead and take a look at some of the applications we'll be using them for. First example, cosine of 15 degrees. 15 degrees is something we cannot look up on our table of values. It's not something that you'll find on the unit circle. It's not a 30 or 45 or 60 degree reference angle, but I could rewrite the cosine of 15 degrees as the cosine of 30 degrees divided by 2. Okay? And now I can use a half angle formula because this is written as a half angle. The half angle formula for cosine is plus or minus the square root of 1 plus the cosine of 30 degrees, all divided by 2. See, I can look up cosine of 30 on my table. I know what that ratio is. That allows me to find an expression that works. There are two important decisions that we need to make on every single one of these problems. And one of these decisions involves what's happening on the outside of the function. What's happening right here? Are we going to pick a positive ratio or a negative ratio? The second decision has to do with what am I plugging in to the inside? Is it going to be a positive ratio or a negative ratio? The first decision, you just have to keep this straight, is always based on the original ratio that we're looking for. What is the angle and what is the quadrant that we end up with, and then what is it cosine, sine, or tangent, and do we have a positive or negative value in that quadrant, okay? The inside one is actually much more straightforward. It's just based on what you see, okay? So if it's going to be positive or negative, it's just going to be based on exactly what we see right there. And with that being said, the cosine of 30 degrees, if you looked it up on your table of values, is root 3 over 2. And because 30 degrees is in quadrant 1 and cosine is positive in quadrant 1, it's a positive root 3 over 2. Now, realistically, we don't usually write a positive when it's positive, but if you wanted to throw it in there just for the first step, there'd be no harm in that, okay? So that's the first decision. The second decision is coming from the outside, and actually it doesn't matter what order you make these decisions in. Usually I do the outside decision first, but the outside decision is based on what is cosine of 15 degrees. Well, 15 degrees is also in quadrant 1, and because I'm looking for the cosine of that, cosine of 15 degrees, cosine's positive in quadrant 1. Once again, you don't have to write that positive there, but if you wanted to for the first step, just to keep your thinking straight, no harm in that. Once you've substituted your ratios and made your two positive or negative decisions, you're really done with the trigonometry part of this problem. That is the end of the trigonometry. The rest of this problem becomes purely algebraic. The first thing I would do is I would try to get rid of the complex fractions by looking at, for any denominators, like this 2 right here, and multiplying by that value. So we're going to get, let's see here, distributing, I'd get 2 plus the square root of 3 all over 4. And here's the beautiful thing about this particular value. Once again, I'm going to use an algebra property that says that if I divide root a by root b, the answer is root a divided by b. You can write it as one root. You know, in Algebra 1, sometimes you may have done problems where it was like, what's the square root of 21 divided by the square root of 7? Well, these are both nasty irrational numbers, but if I rewrite it as the square root of 21 divided by 7, it's actually just the square root of 3. A root divided by a root is a root. And that's pretty much the premise we use a lot on these half-angle formulas. So I'm going to write the square root of 2 plus root 3 in the numerator divided by root 4. And the beautiful thing here is that 4 is a perfect square. And so we're just going to get a 2 on the bottom, which means I don't even have to rationalize it. That's my answer. That's the ratio right there, square root of 2 plus root 3 divided by 2. That is the answer for the cosine of 15 degrees. Similar problem, sine of 5 pi over 8. Of course, it's in radians, so it looks a little bit uglier, but we're going to rewrite it as the sine of half, doubled that value. 5 pi over 8 doubled is going to be 5 pi over 4, and then we'll take half of that to get back to the original ratio. So 5 pi divided by 4 divided by 2 is 5 pi over 8. But the advantage of writing it this way is I don't know much about 5 pi over 8. It's not from the unit circle. But guess what? 5 pi over 4 is. It's a pi over 4 reference angle. So here is my substitution in the formula, cosine of 5 pi over 4. And once again, the beautiful thing here is, didn't know this, I do know this, and I can use it in the formula to solve for what basically goes all the way back to the original question. Okay? So remember what I just talked about on the last problem. Every single problem, we're going to need to make 2 important decisions regarding positive or negative. I mean, you can look up here at the cosine of 5 pi over 4 and know that that's a pi over 4 reference angle, and cosine of pi over 4 is root 2 divided by 2. That's simple enough. But what quadrant is 5 pi over 4 in? Well, 5 pi over 4 is in quadrant 3. And cosine, which is an x value, is negative in quadrant 3. So if this is positive or negative, we have to kind of base it on what we see right there. And in this case, it's negative. Okay? So that's one of those decisions we make. The other decision, of course, the outside decision, should we choose positive or negative out here? That goes back to the original problem. 5 pi over 8, well, let's see here. We know that halfway around the circle is pi, but if we write that as 8 pi over 8, it's a little bit easier to compare. A quarter of the way around the circle is pi over 2, but that might be written as 4 pi over 8. So 5 pi over 8 is going to fall right in there into quadrant 2. And sine, which is kind of based on a y value, is positive in quadrant 2. So if you want to write the positive just to keep you straight on the first problem, that's fine. You don't really need to write that positive out there, though, when it is positive. There's your 2 important decisions. One inside, one outside. And now we're ready to do a little algebra and finish this problem off. And once again, going to eliminate the complex fractions by multiplying the top and the bottom by 2. I'm going to get 2 plus, I'm subtracting a negative, so I'm going to add 2 plus root 2 over 2. Oops, not over 2. 2 times 2 is 4. Now, I know that once I split the fraction and have the root on top, 2 plus root 2 in the numerator, that the square root of 4 in the denominator is going to be 2. And that's your answer. The square root of 2 plus root 2 over 2 is the ratio you would get when evaluating the sine of 5 pi over 8. The last example is probably the ugliest just because it happens to be a tangent ratio, and that formula is just a little bit nastier because we get trig ratios in the denominator as well as the numerator. I'm going to write the angle 112.5 as a half angle. I'm going to make that into 225 degrees divided by 2, which is a 45-degree reference angle, which is why I know I can do this problem. This is equal to plus or minus the square root of 1 subtract cosine of that angle. Remember, we're always using cosines in the formulas. Over 1 plus the cosine of 225. Okay? Sorry about the pen sticking there a little bit. It's a little slow. It doesn't look like cosine 225 on the top. It actually looks like a cosine delta or something. I don't know what it is, but I think you get the point. All right, let's make a couple of decisions, shall we? Let's see here. One of the decisions is going to be whether this is positive or negative out front. One of the decisions is going to be about whether these ratios are positive or negative. Cosine of 225 is a 45-degree reference angle, which is, root 2 over 2. We know that that ratio is going to be root 2 over 2. The question is if it's positive or negative. Well, the outside decision goes back to the original problem, right? And tangent is what in quadrant 112.5 degrees? 2. 112.5 degrees is in quadrant 2. What is tangent in quadrant 2? It's negative. So we're going to get a negative ratio for this answer. Now, as far as the interior of our root goes, we've got cosine, once again, in quadrant 3, which we just had on the last problem, which we said was negative. So that's where we are. And that ends, once again, the trigonometric part. You guys don't have to draw these lines. In fact, don't draw these lines. I'm just trying to make a point that really only the first couple steps are trigonometry. After this, there's just a lot of algebra that we have to do to check what's going on. When I get rid of the denominators or the complex fractions within this fraction, what I'm going to end up with is a negative square root 2 plus root 2 divided by 2 subtract root 2. Now this is where it's a little bit nastier of a problem. We're actually going to have to rationalize that 2 minus root 2 in the denominator, which is a little bit harder than the previous problems. In fact, a lot harder. I'm going to show you two methods here really quickly. The first method is going to be, well, okay, I'm going to show you the same method. I'm just going to show you two different algebraic ways to simplify it. The method is what you learned in Algebra 2. It's using conjugates. The conjugate of 2 subtract root 2 is 2 plus root 2. And so I'm going to multiply both the top and the bottom of this fraction by 2 plus root 2. All right, and this is all under the square root sign, and that's kind of what it looks like. Here's how I'm going to show you two different methods. It's just a way of simplifying two different ways, all right? The first way, we're going to go ahead and really expand that top multiplication. We're going to expand that out. So we're going to get 2 times 2 is 4, and 2 times root 2 is 2 root 2, and we're going to get another 2 root 2, and then root 2 times root 2 is 2. And then on the bottom, this is why we use conjugates, we get difference of squares. The middle terms cancel out, but we get a 2 times 2, 4, subtract root 2 times root 2 is 2. Okay. Where do we go from here? Well, we're going to simplify a whole bunch. We're going to get 6 plus 4 root 2 divided by 2, which I can then factor out a 2 from the top, giving me 3 plus 2 root 2 over 2, and the 2's cancel, and I get negative square root 3 plus 2 root 2. That would be my final answer for that. So as you can see, quite a bit more algebra going down. Here's the other way of doing it. It's a little bit more elegant. We still have the negative, and we saw the square root. And in the denominator, I actually still have 4 subtract 2. I mean, I still get the difference of squares. But here's where it's different. In the numerator, I'm going to get 2 plus root 2 quantity squared. See, I'm looking at it in just a different way. Rather than distributing it, I'm realizing I'm multiplying a binomial by itself. 2 root 2 and 2 root 2 are the same thing. Another way of writing that is 2 plus root 2 quantity squared. Why is that kind of a good deal? Well, here's why it's a good deal. Because square rooting and squaring are inverse functions. They cancel each other out. And that's exactly what's going to happen right here, where the square root sign on the top, at least, is going to cancel the square root sign on the bottom. Maybe we write this one a little more carefully just this first time through so we kind of see what's going on. We're going to break the fraction up into this divided by this, right? So I just split the fraction. And now we can see quite clearly that this root is going to make that square go away, and all I'm going to get is 2 plus root 2 in the numerator and a root 2 in the denominator. Now, this still needs to be rationalized, so there is actually another step here that we're going to have to deal with. We're going to have to multiply the top and the bottom of this guy by root 2. Distributing is going to give me 2 root 2 plus 2 divided by 2. That means I can factor out a 2 in the numerator, which cancels with that 2 in the denominator. So in the end, all I have is a negative quantity 2, root 2 plus 1, or, you know, you certainly are welcome if you wanted to distribute that as writing it as negative root 2 subtract 1. These are the same. And it looks very different from the answer we got over here. Look at this. These things look different, don't they? The values that you're going to find, though, are the same. Look, here's the answer here on the calculator. And look at the ratio we get. Here's the answer we got here on the calculator. Here is the answer we get. Exactly the same ratio. Either one is acceptable. Either one is a rationalized answer. The black answer, the negative square root of 3 plus 2 root 2, is a little bit uglier because it's a complex root, a root within a root. But it's really nothing wrong with it. The tricky thing is, what if you had a multiple choice question? Which way would your answer come out? The way that I believe I've seen them more often is this way right here. This is the way that I've seen more often as answers on multiple choice tests. So keep that squaring the root thing in mind, writing it like this, and that may help you down the road. Okay, last example, and it's a non-known angle problem. It's an angle we don't know. We're just calling it theta. But they give us some clues about theta. So it's very similar to some of the problems we've done previously, where we build triangles to determine ratios, and then we substitute ratios into formulas. So they tell us that cosecant is negative. Cosecant is based on y. It's the reciprocal of sine. And so if cosecant's negative, we certainly can't be above the x-axis where cosecant's positive. We also know tangent is positive, which means we're going to be over here in quadrant 3, because tangent's only positive in quadrants 1 and 3, and we already had eliminated 1. Let's see here, the hypotenuse over the opposite is 5 over 3, with one of those values being negative. Remember, the hypotenuse is a distance and can't be negative, but the negative 3 is certainly down into the negative direction. And then this is a 3, 4, 5 primitive, and make sure you remember that your adjacent also would be negative since it's to the left. The only ratio that I need, the only one that I need to apply a half angle formula is the cosine ratio. And that's going to be negative 4/5 based on this triangle. Okay? So now that I know the ratio I need, let's go determine what we want. We want the sine of pi over 2. And I know the formula for the sine of pi over 2 is plus or minus the square root of 1 subtract cosine of theta over 2. I think I said pi over 2 repeatedly there, which is really weird. What I meant is theta over 2. The sine of theta over 2 is plus or minus the square root of 1 subtract cosine of theta divided by 2. And our theta value is negative 4/5. The nice thing about doing this kind of a problem is that you built the quadrant, and as long as you were careful labeling the sides of your triangle, the signs take care of themselves. You know that inner sign is going to be negative because you already did the work building the triangle. We do still have to think a little bit about this outside sign. Okay? And this is where things get just a tad bit tricky. And so here's what I want you to consider. All right? Look at this little drawing. We know that we have 4 quadrants, 1, 2, 3, and 4. And that's what I'm going to call the theta axes, okay? Here's our theta over 2 axes right here. And what the theta over 2 axes is going to do is it's going to take each of the quadrants from the theta axes, it's going to cut it in half. So if previously we were going from 0 to 90, and then I divide this angle by 2, what's going to happen? Well, 0 divided by 2 is still 0, but 90 divided by 2 cuts me back to 45. So what this basically means is that if your theta angle is in quadrant 1, then your theta over 2 angle would be in the first half of quadrant 1. It would be between 0 and 45 degrees. All right? Now, continuing on with this same concept, if theta was in quadrant 2, so between 90 and 180 degrees, and we divided that in half, 90 divided by 2 is 45 again. 180 divided by 2 is 90. And so any theta angle that was in quadrant 2, if it was divided by 2, would get sucked back into the second half of quadrant 1. And if we continue doing that, what we would realize is that anybody in quadrant 3 would be between 90 and 135 degrees. So your half angles would be here, and anybody in quadrant 4, which would be between 270 and 360 divided by 2 would be 135 and 180. So this would be your quadrant 4. So you end up kind of with a picture that looks like this. Okay? Now this is only for one full rotation. Usually your hints are, you're between pi and 3 pi over 2, or you're between pi over 2 and pi. And so this tells you that if your full angle, if you're building your triangle, if you just built your triangle in quadrant 3, and that's where theta is, if you're trying to determine if it's positive or negative, your theta over 2 would actually be back in quadrant 2. And so that helps you decide where these things are going to be positive or negative. So if this hasn't confused you enough, let's go back and finish our problem. Okay? We are dealing with a sine graph. The angle is in quadrant 3. Okay? That means our theta, and remember this is based on rotation theta. So theta is between, let's just use degrees. Theta is between 180 degrees and 270 degrees. So if we divide that by 2 because we want it divisible by 2, or we want half the angle, I should say, then everybody gets cut in half. Okay, that's how you work with inequalities. Each part of the inequality gets divided by the same value. Well, that's going to put us back between 90 and 135. Okay, which, remember, was in the first half of quadrant 2. That's what the pictures we were just looking at a couple minutes ago were telling us. So that's just how you can kind of determine, hey, where is the half angle compared to the full angle? Well, we were doing sine, right? We were doing sine, and we know it's back in quadrant 2, and sine in quadrant 2 happens to be positive. That's how you get that sign. So don't base this on the quadrant you're drawing it in. That's bad. Bad. Base it on the half angle. What is half of the quadrant you're drawing it in? Okay? And so either those little pictures or the inequality thing, those would help you. The rest of this problem is just simplifying the radical. We're going to multiply by 5 on the top and the bottom. We're going to get the square root of 5 plus, because remember I'm subtracting a negative, 4 all over 10. Let's split this root up into, how about a root 9 divided by root 10? Well, that's just going to be, well, I'll go ahead and rationalize it for you. We're going to multiply by root 10 over root 10. So our final answer is going to be 3 root 10 over 10. That is your answer for this last example. The hardest part, the most often missed part, you're just going to have to trust me with this, is this right here, picking the right side. Okay, this is where people make their mistake, because they just make that decision based on the quadrant you drew the triangle in. You got to remember, though, that the quadrant you drew the triangle in was based on an angle theta. Okay, it was based on this angle right here. Look, that's theta. Okay, and look, the other clue based on theta. These clues are based on theta, but that's not what you're trying to find the ratio for. You're trying to find a ratio for theta over 2. But you always have to go halfway back to figure if you should be positive or negative. A little bit confusing, I know. So just pay attention to it. You'll do fine on these. There are some problems to take a look at and practice, and I hope you guys do well. Thanks for watching.